in this segment, I want to tell you about a little lemma. What it says is that if you have an infinite set and you add countably many things to that set, you will not change the size of your original infinite set. So let me go through some definitions to make clear exactly what I mean. So for a set A to be countable is for there to be an injection from it to the natural numbers. And for a set to be infinite is for there to be an injection from the natural numbers to it. So anything smaller or equal in size to the natural numbers is countable. Anything bigger or equal in size to the natural numbers is infinite. And anything of the same size as the natural numbers is both countable and infinite. And here's what our lemma says. It says that the size of an infinite set is exactly the size as a result of putting together that infinite set with some countable set. So here I is infinite, C is countable. And I'm going to simplify things a little bit by assuming that I and C have no elements in common. That actually makes no real difference. No real generality is lost, but it'll simplify the proof. OK, so here is what we need to show in order to prove that this is true. We need to find a bijection from our set I to the union of I and C. And the way we're going to do it is by taking advantage of the fact that I is infinite, and therefore that there's an injection from the natural numbers to it. So here we have the natural numbers. And we know there's a function that maps 0 to something, and 1 to something, and 2 to something, different natural numbers to different elements of I. And let me just call the range of that function R. There might be things outside R, and indeed, there might be a very large infinity of things outside R. R itself is going to be a countable subset of I. And then we're going to define our bijection as follows. So we're going to define a function from I to the union of I and C by saying that f of x is just x when x is outside R. So if you take something that's in I but outside R, then we just map it to itself. This is our function f. And then what we're going to do for elements of I that are inside R is that we're going to find a way of mapping them not just onto R, but onto R union C. And the way we're going to do this is by using Hilbert's hotel. So let's draw our infinite hotel. Which has one room for each natural number. And we're going to start by populating our hotel with the elements of R. So say that 0 gets mapped to R0 and 1 to R1 and 2 to R2 and so forth. So then let's just put R0 in room 0, R1 in room 1, R2 in room 2, and so forth. And now what we're going to do is we're going to move around the inhabitants of our hotel so that we can also make room for the people in C. So here we have our rooms again. And the way we're going to do this is by noticing that it's possible to assign a natural number to each element in C. The reason for this is that we know that C is countable, and therefore that there's an injection from it to the natural numbers. So we can let the first element of C, C0, be whichever element of C is mapped onto the smallest natural number, and C1 be the element of C that's mapped onto the next smallest natural number, and so forth. Now, there are two cases to consider. The first case is the case where C is finite. In other words, there's a biggest member of this sequence. Let's call it Cn. And then what we can do in order to accommodate all the elements of C into our hotel is just ask the R's to move n rooms to the right. So R0 moves to room n. That leaves n rooms free, and we can accommodate the members of C. Now, the second case to consider is the case where C is infinite. But when we discussed Hilbert's hotel, we saw how to accommodate a countably infinite set into our hotel. What we do is we ask the inhabitant of room I to move to room 2I. So R0 stays in room 0, R1 moves to room 2, R2 moves to room 4, R3 moves to room 6, and so forth. That leaves all the odd numbered rooms free, and we just use them to accommodate the elements of C. We put C0 in room 1, C1 in room 3, C2 in room 5, and so forth. We are now in a position to define a function g from the elements of R to the union of R and C. So function g, which just takes each element of R to the new occupant of its room. So R0 goes to R0, R1 to C0, R2 to R1, and so forth. So going back to our diagram, what this means is that G maps R0 to R0, R1 to C0, R2 to R1, and so forth. We keep alternating. So we call this function g. And now we can complete our bijection. We can say that f of x is just g of x when x is a member of R. So we have successfully characterized a bijection from I to I or C. The way our bijection works is it's the identity function when it comes to members of I which are not in R, and it's our function g when it comes to elements of I, which are also in R. So we've proved our lemma. If you take an infinite set, no matter how big it is, and you add countably many things to that set, that will not change the size of your set.